and we've got a whole series of things happening about time. Do take a leaflet on your way out about time. There's a lecture series, and also we're having once a month a session on various doctors from the Doctor Who series, which I think has attracted a lot of interest, so please do take one of those. It's a great pleasure to welcome tonight, if I can find him on here, there he is, to welcome tonight David. I knew your name really, I was just trying to call up what you've actually done. David studied natural sciences at Cambridge, and also gained his PhD from there in astronomy, and has been in Portsmouth for about 10 years, both as a senior research fellow and as a reader in astronomy. And he's going to share with us some of his thoughts about time in the universe. I'm absolutely fascinated by time. I once read Stephen Hawking's A Brief History of Time, and I suppose I understood about a quarter of it, which I think is quite good actually. But I'm hoping you'll help me through some of the difficult concepts in it. So David's going to talk to us and then give time for questions, discussion, etc. So David, welcome. Lovely to have you with us.
Very much. Thank you. So it's a pleasure to be with you tonight and to talk to you about this very staggering subject of time in the universe. Recently we had an open day at the university where 17-year-olds come and look around and they ask us questions and they're interested in whether they're going to come to Portsmouth University to study. And I got a question from this particular 17-year-old young woman, which I think is one of the best ones that I've got so far. Normally they ask about, is it a good city to cycle in, or what do I do about accommodation? But this young woman said, do you, as an astronomer, just live all of your life with this sense of fear and fright about how big the universe is? And I said to her, well, actually, most of the time, no, but occasionally, yes, and it creeps up on you when that's going to be. So sometimes I go to a talk and someone says something like, oh, this is only a small galaxy, it's only a few thousand light years wide. And suddenly you think, a few thousand light years wide, that means that light itself would take thousands of years to go across this particular object. You think this is an astonishing and awesome and possibly intimidating place to be, this universe. It's absolutely massive. But there's more to it than that. We don't have to be constantly frightened of it. After all, it is our home. So let's have a think about time in the universe. The first question, I guess, is what is time really? Some of you will have come hoping that I can tell you at bottom what exactly is time. And that's a very hard thing for anyone to answer. It's very hard for a scientist to answer. Probably a better approach, and somewhere where I can start, is to talk about how does time behave? How do clocks behave in the universe? We can start to give some good answers to that. But what is it really at the very root of things? That's much harder to deal with. Someone who thought a lot about this was St. Augustine, who at the time of 400 AD wrote a very famous book, his Confessions, which has got some extraordinary insights into time and human psychology without any of the benefits of modern science that we now have. And he said this, what then is time? If no one asks me, I know. If I wish to explain to him who asks, I know not. And that's probably how we all feel, including me, when we think about time. It seems something which is intrinsic to our experience. When we get to science, it seems to be something which is intrinsic to our scientific theories. But what it actually is, well, that's something that we're still struggling to describe. By the way, will there be a possibility of losing those lights, I wonder? Because at some points it might get a little... That's great, that's perfect. Thank you very much. So when we think about space and time, perhaps it's useful to start by thinking about this cathedral. And when we look from the nave through this impressive space, we see different regions, different periods of history where this cathedral was built. There's parts of the chancel which are 12th century, then there's the rebuilding that happened in the 17th century, and then all of the beautiful new development in the last 30 years. And so where we are situated in this photograph, as we look further away, we start to see things which are further back in time. And that is a very rough analogy to what you'll see is true of the universe. But this also makes us think about our emotional relationship with space and time. In this particular case, such a beautiful, massive building evokes our sense of awe. It also isn't necessarily a frightening experience. It actually helps us to connect with the fact that there's all of these other times. We feel that we're part of something that's been going on for a very long time. So there's positive ways of thinking about it. Now let's think about our universe. So in this animation that I'll show just now, in a moment the camera will pan round and you'll see the Earth and the Moon and our star, the Sun, and then we'll zoom out further and further into the universe so that we can get a sense of what we're talking about when we're describing this universe known to physics. And as we zoom out, we're also going further and further back in time. So let's see how it goes. There's the Earth and the Moon. There's our star, the Sun. And if we zoom out further, we see that there's other planets around our star. There's Jupiter and Saturn. And we keep zooming out further, and we get beyond our particular star, and we see that there's many other stars too. And also these gas clouds, like this one here. And if we zoom out further, we see that all of these stars, including our Sun, make up the Milky Way galaxy, made of 100 billion stars, such as our Sun, or 200 billion stars. Here's our sister galaxy, Andromeda, and then we zoom out even further and we find that there's hundreds of billions of other galaxies, each made of hundreds of billions of stars. Now we're getting towards the beginning of time, where stars have not yet started to shine, and then if we go back even further, we get towards the very beginning, when the baby universe is just full of very, very hot gas. And then if we zoom out even further back in time, we get to the stage at the very beginning, where we can say no more from physics. That's our universe, and you can see that time is going to be a very important aspect of understanding it. But let's start with something more nearby. So here's our solar system. There's our star. It looks absolutely massive on this image because we live so close to it. Here we can see all of the different planets which are orbiting our star. And the important thing to realise about light coming from this star is that it does travel with a finite speed. It doesn't just travel zoom infinitely fast. It actually takes time for light to come from the sun to these different places. So we don't see what the sun is like right now. We see what the sun was like when the light set out. And it came to us and we see it. So here's a little quiz. How many minutes do you think it takes light to get from the sun to Mercury?
8.
Good guess, good guess. The answer is 3 minutes to get to Mercury. And then to Venus, it's 6. To Earth? 8. Well done. So that is to say, if something catastrophic happened at the surface of the sun right now, well, we're on the wrong side of the Earth, but let's suppose it was daytime. Right now, something has happened which is catastrophic on the surface of the sun. We're safe and ignorant for another 8 minutes. In other words, when we see this catastrophic event in 8 minutes' time, we're looking back in time. We're looking at what the sun was like 8 minutes ago. We don't have access to what the sun is like right now. Let's keep going. Mars is 13 minutes from the sun, the light to travel to Mars. Jupiter is 43 minutes. Saturn, any guesses?
57.
Oh, that's pretty good. is 79. So what this means, now let's think about light travelling a different way. We know that there are lightning flashes on Saturn, we've observed them. And suppose you get in one of these storms on Saturn a lightning flash, well, it will take an hour or so for us to know about that. So we're looking back in time an hour when we see lightning on Saturn. And so on, 160 minutes to Uranus and 250 minutes to Neptune. So it takes hours and hours for light to travel from the edge of our solar system to us. Now we can go further and start to feel the oddness of this fact that the further away we look, the further back in time we're looking. So let's think about a time which is important to this cathedral, 2,000 years ago. So if we think about light travelling for 2,000 years, there's a peculiar connection that you can all make between the night sky and the birth of Christianity. Here's Orion. You've probably all seen it. It's a constellation which is visible if the cloud gets out of the way tonight in the south behind the cathedral. And here's Orion's belt. This is a beautiful image of those three stars in Orion's belt. They're called Alnitak, Alnilam and Mintaka. If you look at the middle star of Orion's belt tonight or soon, you are directly looking at light from the time of the birth of Christ. It's 2,000 light years away. Give or take 10 years, right? It's a very extraordinary thing, very strange, that when we are looking at that star, we're not seeing it now, we're seeing it at the time of 2,000 years ago. It's also fun to think about what could be true of Mintaka, because Mintaka is a little under 1,000 light years away. What that means is that the light from the time of the Roman Empire, from the time of ancient Judea, will have travelled out from Earth and got to Mintaka about 1000 AD. And if there's any aliens there with their telescopes, they could have taken a nice photograph of the Mediterranean, and now they have time to have sent it back to us, because they've had another 1,000 years of light travelling to come back. So if you want to try on the off chance to intercept a photograph of the ancient Middle East, that's a good place to look. It's a very, very strange thing that we're looking back in time in these ways. And when you start to keep going with this game, you start to realise how vast the universe is and how vast its time is. Here's our galaxy. It's an artist's impression. We can't take this photograph because we're within it, but it's accurate in terms of where we know the star positions to be. And here's where the sun is, just here. The whole galaxy, well, from there to here is 30,000 light years. That means it takes light 30,000 years to get out to that. Or over to that way, it's 75,000 light years. So if we ask, how far has the light travelled through the whole history of Christianity? So, if you like, the message of this religion, how far could it have travelled? The answer is alarmingly that. In our own galaxy. And this is only one galaxy of billions. So that really is mind-boggling. If instead of the last 2,000 years we ask about the whole written history of humanity, which is about 5,000 years since we've got records, human recorded history, then it's that, which is still very modest. So in other words, for most of the galaxy, they are unaware, they remain unaware that there is written history on this planet. Even if we'd sent it out 5,000 years ago and we didn't have the radio telescopes to do so. If you're talking about the history that surveyed the region where our radio telescopes would have broadcast to, or our radio transmissions would have broadcast to, of course that's just a tiny region of the last 50 years, so a 50 light year radius. The stars in here would have heard our signals. So it's really remarkably huge, what we're talking about in our universe. Here we've stopped looking at one galaxy, and every dot on this plot is a real galaxy. So now, this is a dot-to-dot diagram of where there are galaxies in the universe. And there are regions where there are many galaxies, there are also regions where there are hardly any. And this is not the whole universe, this is just a particular survey of the three-dimensional positions of galaxies out for about 1 billion light years. So the whole universe is much bigger than this. Why is it like pizza slices? Well, it's just because the survey looked at that bit and then looked at that bit. It doesn't mean that the universe is really empty over here, it's just we didn't look there. And Portsmouth, our department in Portsmouth, the Institute of Cosmology and Gravitation, have been one of the leading institutes in working with this survey. It's called the Sloan Digital Sky Survey. And on this sort of plot, we can ask, how far out has the light from the dinosaurs got so far? And the answer is merely that. So that's a 200 million light year radius. And again, only the very nearest little bits of the pattern would actually have got the light from our past. So it's surprisingly huge. Let's now focus on this web, because this web is very useful for us to start to understand how old is the universe overall. It's got a particular pattern in it. It's not just at random. It looks like there's knots of galaxies and then strands of galaxies and then big holes where there's voids going on for hundreds of millions of light years. And we can ask, how did this web form? It turns out that there's a very quite simple way of making a web like this in a computer. What you do is in your computer code, you make a box and you fill it with a type of little bits of dust, tiny little particles of material. And then what you do is you just allow the law of gravity, Einstein's law of gravity, to be present for all of the little bits of dust. So all the bits of dust feel gravity for all the other bits of dust. And you see what happens. This is what happens. At first, it just looks like a nice smooth cloud of dust. And then as time goes on, some bits of dust are a bit closer to other bits, so they tend to come together, and then that means more dust comes to that bit, and more comes to that bit, and more comes to that bit. And so some regions evacuate, and some regions become pronounced. And in the end, you get this sort of pattern, where there's this web of material that forms from a very simple situation at the beginning, where there's just a smooth amount of dust-like particles. So when you do that in a computer, with our law of gravity, you find that the time it takes, the simulated time it takes in your computer, is well, up till now it's about 1 billion years. It doesn't take 1 billion years for your computer to do it, but that's the simulated time for it to come to this sort of pattern. And eventually you get, after 10 billion years, you get these sort of patterns. Now, I always forget which is which. Red or blue is real dot-to-dots of where galaxies are, and the other one is the simulated ones. And I think you can see that the patterns are very, very similar. So this simple bit of physics that went into the simulation really did make a pattern that's very close to realistic. It turns out that red, I can read it now, red is the simulation and blue is the real data. And it turns out that to get the patterns that similar, you need a simulated universe that's about 14 billion years old. This is one of the reasons why cosmologists like me put that sort of number on the age of the universe. Let me move on. There's more I could say about that sort of thing, how you measure time, but maybe I'll leave that for the questions later. So this is the sort of story that that cosmologists have come up to about the history of the universe. So here's that satellite again. This is the present day, and it's looking back at the whole story. And here we have the very beginning. We'll come back to that in a second. soon after that, there's this gas, this very hot gas. Then there's a region where there's a dark age, where no stars have yet started to shine. And then the galaxies, the stars in the galaxies start to shine, and all of the material collapses into this web in the way that I just described. So that's the story. And at this stage, I expect that there are people in the audience who are religious and who are not religious. And you may be wondering, how does this fit with your own personal beliefs? And I want you to have a think about that. I think about it myself with my own personal beliefs. I'm a Christian and a scientist, and I have to think about how these things relate. But one thing to say at the beginning is that certainly some of the scientists who've been responsible for this type of picture of the universe have not found a clash between it. So, for instance, the person who proposed the Big Bang, which is what we have here starting the universe, do you know who it was? Do you know the person who proposed that? It's a scientist called Georges Lemaitre, who was a Roman Catholic priest. And so he, as a priest, proposed this idea that the universe started very, very small and hot and developed out from there. In fact, the Pope in 1950 suggested that this new Big Bang theory was a confirmation of the Christian story. And interestingly, Georges Lemaitre was not having that. He didn't think that there ought to be that close a connection between the science and religion. He thought that the two were not inconsistent, but shouldn't be tied together so closely. This is now my own opinion, not his. I'm not sure why he said that, but my own opinion is it's something of a hostage to fortune to tie them so closely, because, for instance, in the future we might find that this Big Bang is not the beginning of everything, it's just the beginning of our epoch, and that there are other things before that. So one has to be careful about seeing too close a relationship between religion and science, but nevertheless there can be a very productive and friendly relationship between them. At least that was his view. Okay, so that's everything I want to say about the age of the universe and this vast period of time that has happened in the universe. So that was my first point, that time's extent is amazing. There's something else that's extremely odd about time in the universe that we know a lot about as astronomers, and that's that the flow of time is not constant everywhere. We tend to think of time as just something that flows on and we're all going to experience it at the same rate. That seems like common sense, and for all of us in the room, it is happening right now. We're all psychologically we may experience it at different rates. Some of you may be watching the clock because you're desperately bored and it goes on and on and on forever. But that's a psychological effect. I'm not talking about that. I'm saying that if you've all got clocks, and we compare all of your clocks, and if your clocks are good, then we'll find that you all agree that the same amount of time passed during this talk. But that's not necessarily true in different parts of the universe and for different observers at different places in the universe. There's two ways in which the flow of time can change from place to place. So the first and second, actually, are due to Albert Einstein's understanding. So he proposed these things, and they've been confirmed experimentally. So the first thing that we want to talk about is that the rate of time observed depends on how fast someone is going. That seems very strange, and let me tell you what I mean by that. Do you like my awesome image of a rocket? So we've got somebody moving very fast. This effect is pronounced if the rocket is going near the speed of light, which none of our rockets do yet. But let's suppose it's moving close to the speed of light, and here's an observer, it could be you in this room, and you look at Jill in the rocket. Now Jill is waving, and she's waving at 1 wave per second, let's say, like this. She really experiences it that way. She doesn't think her time is slowed down, she is waving at 1 wave per second. But you, looking at Jill, don't see her doing that. You see her going like that as the rocket goes past. To you, you observe Jill's time to have slowed down. It's a very, very strange thing. Now, you might think, let's think about the other possibility. Suppose you're Jill. You're on the rocket, and of course you see me whip past in the other direction, because you feel as though you're standing still on the rocket and you see everything swishing past. So you might think that she must see me, I'm waving too, 1 wave per second. You might think that she must see me waving much faster, and then that would make sense, right? That I see her waving slower, so she must see me waving faster. But actually that's not true, according to this theory by Einstein. It's called special relativity. Jill sees me slowed down. And you might think that that's just impossible, but actually it does work, that both of them can see each other slowed down. This sort of effect really happens, and you may even have used this effect on your way here tonight. So, for instance, this was tested in an amazingly cheap experiment by 2 scientists in the 1970s, Joseph Hafele, I don't know how to pronounce his name, and Richard Keating. And what they did was that they proposed that they got $8,000 worth of funding to buy plane tickets, commercial plane tickets, and on the plane they'd booked seats for themselves and also a seat for a big clock, an atomic clock. Here it is. This is really what they faced, and they went on a round-the-world trip on this aeroplane. The idea being that the aeroplane is like our rocket. Okay, it's moving fast. So if this theory is correct, what this would mean is that the clock on the plane should appear to be ticking slower compared to one that was left on the Earth. So they had an atomic clock in a laboratory in the United States. They also had 48 hours of taking the clock around in a fast aeroplane, and they did indeed find that the clock on the eastbound aeroplane ran slow by 60 nanoseconds, that's 60 billionths of a second, over a 48-hour journey. Like I say, this effect is most pronounced if you're moving really fast, the speed of light, but it's detectable if you're moving the speed of an aeroplane. And why I say that you've probably used this effect on your way here is that there's a very similar issue with Global Positioning System. So if you've been using GPS to find your way here, it turns out that without this effect, the GPS would get it wrong by 10 kilometers a day. So you soon realise that your GPS was directing you to Southampton rather than Portsmouth, unless you take into account this effect, that because the satellites that the GPS is using are moving fast, and therefore their clocks are ticking at a different rate to on the Earth. There's another example of this, which is that all the time our atmosphere is being bombarded by cosmic rays, and what happens is, as they hit the atmosphere, they create lots of particles. Some of them are called muons. Muons are quite short-lived. They live for 2 microseconds, 2 millionths of a second. And how far they could move in 2 millionths of a second is not very far, a few hundred meters. So if they start there, and they just can move a few hundred meters before they die, that means they decay to some other particle, then we'd never see them. But we do see them. We detect lots of muons on the surface of the Earth. How can that be? It's because they're moving quickly, so their clocks are slow. So they think, they don't have any more fun, they think they live for 2 microseconds, but they actually live for maybe a factor of 10 longer than that, and they can therefore travel all the way to the Earth. It makes them long-lived. So this really is happening all the time. One more example, which is kind of fun. If what I'm saying is correct, and it is, then let's think about 2 twins. And one of them will stay on the Earth and work in an office, and one of them will go in a super-fast rocket and do a tour of the solar system and then come back. And the tour is, well, it's going to be larger than the solar system. It's going to be a 50-year tour as far as Office Man is concerned. It's a really, really fast rocket. So let's think. Office Man is just living as normal, but according to him, his twin, remember, is having his clock really slow, which means that by the time the twin comes back, the twin will hardly have aged at all, whereas Office Man has aged 50 years. Or is that right? Because couldn't you say what I said, that the twin is going really fast, but he sees Office Man zooming off backwards on the Earth behind him. So you'd have thought that that means that he sees Office Man's clock going really slow. So when he gets back, doesn't that mean that Office Man hasn't aged much? What do you think is the truth? I'll tell you what the truth is. I don't have time to explain it now, but it's very interesting. The truth is that when you work out what happens, it turns out that the space traveller is younger than his twin. So that seems to be a paradox. It's kind of fun to work out why aren't they symmetric? Why is it that it works that way round? That the one who stays on Earth ages, but the one who travels doesn't. But this is true in the universe too. We see this type of clock ticking slower the faster things go. So an example of this is something we do a lot in Portsmouth. We detect and measure star explosions called supernovae. And we really do see the time ticking slower for these supernovae if we see them far away. The reason that it's interesting that they're far away is because things far away tend to be moving very fast away from us. The further away they are, the faster they're moving away. So then, according to Einstein, if they're moving fast, their clocks will slow down. We really see this. We see that the distant supernovae, these supernovae, they're explosions where you've got a little star here called a white dwarf star with another big star next to them, and it's sucking gas off the big star onto this thing, and this thing goes unstable and explodes. Boom! And it gets brighter and brighter and brighter, like this star here. It can be as bright as the whole galaxy. It gets brighter, and then it gets less bright again. There's a certain amount of time it takes to get bright, and then time it takes to get faint again. And we see that the distant supernovae take maybe twice as long to get bright and then fade again. So it really is the case that the further they are away, the slower their clocks are ticking. Now it may occur to you at this stage to think, okay, so does that mean that the 14 billion years of the universe is an illusion then? Because clocks are ticking slower in the past. That doesn't work. First of all, if the universe was a lot younger, in actual fact, if you looked far away, you'd need clocks to be ticking faster, if you think about it. We can talk about why. But in fact, I've already taken all of that into account when I said the universe is 14 billion years old. Because when I say the age of the universe is 14 billion years old, I mean it's 14 billion years on a clock which we've counted. Okay? I'm not talking about what it looks like, if you want to call this an illusion. I don't think it's an illusion, but we see distant clocks ticking slower. I'm not talking about those clocks. I'm talking about a clock that's been in our back pocket. The other thing that time depends on, so time depends on how fast things are going. It also, interestingly, depends on how much gravity there is nearby. And that's quite strange. Again, it was due to Einstein who realised this. So his picture of what's going on with gravity is a bit like a rubber sheet. Space and time are like a rubber sheet. So if you've got the sun, for instance, it's giving you lots of gravity. It's almost as though it's bending space and time. And when we say bending space and time, we really mean if you're near the sun, your clock ticks slower than if you're far away from the sun. And this has really been found with a satellite where, this is called Cassini, it was near Saturn in the early noughties, and there was a radio signal gone from Earth to Cassini, and it went really near the sun. What was found was that the radio wave ticked slower because it came through this gravity near the sun. So it appeared actually to be a lower frequency, the radio wave, than it would have been normally. So this really does seem to happen. Anyway, so Einstein's picture of gravity is this sort of idea, that if you've got something heavy, it bends space and time. And then you can say, well, what if something's really, really heavy and really, really dense? And then you'd actually almost get a puncture in space and time. It would be massively distorted. And that's what we call a black hole. And so really weird things happen to time near a black hole. So for instance, suppose that we've said goodbye to our dear friend, what name shall I use this time? Something bad is going to happen to this person, so I don't really want to choose a name. Let's call them our dear friend. And our dear friend has decided that they're going to go and get close to this black hole. We're going to stay way out. We're not stupid. We're going to stay way out here. And we're going to see what happens. And again, our friend is going to wave at 1 wave per second. What we see happen is very strange. When our friend is there, way out, away from the black hole, we see them waving at the normal rate. And as they get closer to the black hole, we see them waving slower. And slower still. Until they get to an edge, if you like, a sort of point of no return near the black hole. And we never see them go in. We never see them go in. We just see them waving slower and slower. In actual fact, even the light from them is waving slower and slower. So they go red, and then they go infrared, and then they go radio. So eventually we lose touch with them. But we never see them go in. That's what time is like near a black hole. Nobody has ever seen anything go into a black hole. It's all just stuck at the edge. It's really strange. But if we are our friend, imagine you're the friend now, you see something quite different. If you're falling into the black hole, as I've said before, this person doesn't have any more fun. It's not as though time slows down for them and they can enjoy that fact. It's not like that. So, at first, over here, time is ticking normally, and then they get closer to the black hole and they still think time is ticking normally, and then they get closer, time is still ticking normally, and then they go through. They don't feel that there's a problem, and time still ticks normally when they go through that horizon, and then they die, I'm afraid, in a finite amount of time. There's very different experiences of time for these two people, one way out from the black hole and one way in. Is that a contradiction? No, they would all agree about, for instance, how many waves the friend made before they got to that point, but they'd experience it in a very different way. You might say, oh, that's all fascinating science fiction, but these objects really exist. So 2 years ago now, this amazing new telescope in the United States started working. So this is a 4-kilometre laser, and then another 4-kilometre laser in a different direction. And the lasers are organised in such a way that what you can detect is slight changes in the length of that 4-kilometre arm. And what they're looking for is, I need to get rid of my microphone for a moment. They're looking for slight ripples in space and time. So as ripples in space and time come past, the lengths of space for these two arms will differ slightly, and they can actually try and detect that. So if there's anything that's rippling space and time, these things detect that. And there's one in the northwest and one in the southeast of the United States. So the idea is that if they both detect the same pattern of ripples, that must be something from space. That it's not going to be local subsidence. And about 2 years ago, they detected this ripple with time. This is much less than a second, and the red is one of the places in the United States, and the blue is the other one. They basically agree. When it's all cleaned up, they have this sort of pattern, which fits exactly the pattern we'd expect if two black holes merge. If you get two black holes and they merge together, they do a little dance and spiral into each other, and they make space and time ripple that rubber sheet actually starts to ripple, and the ripples go out all the way to us. So this is what happened. Two black holes, each about the size of Hampshire, 1 billion years ago, did this. They moved past each other, and you can see they're causing these ripples in space and time. And they continued their little dance, and they got so close that eventually you get this dramatic rippling of space, and then they merge to be something 60 times the mass of the sun. They reached about 30 times the mass of the sun, and they merged to make one. And that was 1 billion years ago, and therefore it took 1 billion light years. It's 1 billion light year distance. It took 1 billion years for the gravity waves to get to us. And so this sort of detection means that, yes, these black holes really are existing, and there's now been a handful, I can't remember exactly how many, about 5 of these black hole merger events that have been detected. Interestingly, one of the 3 people in the world who actually eyeballs these events has just moved to Portsmouth to work in our department, Andy Lundgren. He's one of the people who actually detects these black hole mergers. So, on to the last bit of my talk then, which is, how does this all make you feel? How does it make me feel? So let's take both of those parts of the talk in turn. How do you feel about the vast time span of the universe? Maybe you feel neutral about it because it hasn't affected you emotionally at all. But there are just occasions when it really does affect me emotionally. And I've had all sorts of comments from different audiences that I've spoken to about this. So, for instance, very recently I had an audience member who came to me afterwards and said, "You've convinced me that there is no God." Which I was very surprised by, because it's not my view, and it wasn't my intention at all. So that's one possibility. I've also had audience members who express worship to God because of the grandeur of all of this. I've had audience members who suggest that this is in best agreement with Taoism, but most of all, and almost at every talk, I have audience members who ask me if I believe in aliens. It seems to be always the reaction of most people. So does that mean that aliens exist? I'm not quite sure because I haven't mentioned aliens, but you're welcome to ask it if you want. But let's think about our reactions to this vast universe. So first of all, does it bother you? Does it bother you that the extent and influence of human history is so tiny? When I started showing those yellow circles for the influence of everything we've ever known or ever wrote about is so tiny even in our own galaxy, do you find that bothering? I sometimes find it bothering. Or you can take a very different view and you can say, this vast universe inspires awe and even worship. You know, do you find it thrilling? Or do you find both of those things? I certainly find both of those things to be true. I'm not going to tell you the answers, by the way. This is me stirring you up to think about it for yourself. But both of these reactions are not new. We do find it very long ago. For instance, the psalmist says, "When I consider your heavens, what is mankind that you're mindful of them?" And it's interesting to think, you know, is that a cry of despair, seeing the stars? Or is it a cry of wonder? It's certainly a cry of smallness. But the psalmist doesn't finish there. He says, "And you have crowned humans with glory and honour." So it's the mixture of thinking, wow, we're really small, but also this is a wonderful thing. So here's some questions for you to consider. First question for you, feel free, when you're in the Dolphin later or having a cup of tea at home, have a discussion about this. Do you agree that our tiny place in the universe should humble us? I think actually religious people and non-religious people can pretty much agree, many of them will agree with this, that a perspective on the whole universe actually reduces some of our problems to a different sort of level of significance. And if we are this minuscule little creatures, how does that affect how we live our lives? But more positively, you could ask the question, should we measure human importance by its length in space and time? You know, why are you worried? Why am I worried by the fact that we're so small? There's many things where if they're rare and unique and there's not much of them, we actually consider that precious. And maybe that's a different way of thinking about humanity. There's very few places, perhaps, in the universe which are this rich with reflection on what the universe is like. In this little region, a bit of the universe has woken up and has started talking about what the universe is like. Maybe that's remarkable and precious, even if it doesn't last very long in the grand scheme of things. And the other thing is, you know, why worry about the vastness of time? We can, who says that we have to think that the big picture of time is the most important thing? Why can't we focus on human lifetimes and days and moments and say that that's what's important about the universe? And the other thing, of course, that you may want to consider, given this cathedral series, is do you think this story of the universe has religious implications? And you may think that it has negative religious implications or positive ones, and that's worth considering. And then the second part of the talk was this weird stuff about time, depending on how fast we're going and how much gravity there is. And is there anything that we should be thinking about the meaning of that? I'm much less clear about this. It is really strange. The things I've been saying about falling into a black hole or all of these paradoxes, it is very strange. The worst, in my opinion, conclusion that you could draw is, oh, that means that everything is relative and that there's no truth, we're into the era of fake news. You know, whether you fall into the black hole or not is just a matter of opinion or whoever speaks loudest. That's not what we're saying. That's not the type of relativity we're talking about. It doesn't mean that events aren't real. Like I say, everybody agrees about how many waves the friend made before they fell in. But their experience of it is quite different. So it's more like seeing an object from different angles. I see my laptop from this angle. It allows me to see certain things about it. You see my laptop from a different angle and you have a different perspective on it. It allows you to see different things. It's more like that. In fact, mathematically it's more like that. It's more like rotations than it is saying maybe the laptop's there or maybe the laptop's not there. It depends on your point of view. That's not what we're saying. But it does open up new ideas about time, doesn't it? It's interesting that time doesn't run at a fixed rate. It does depend where you are and who you're comparing to. So, I think I've gone on for long enough. Let me just finish with a summary. So this is what I've been saying tonight, that time in the universe is staggeringly vast, and we have lots of evidence for that. The time you observe depends on speed and gravity, which is quite a strange result, which we're seeing over and over again in different situations in the universe. And I hope I've stirred you to think about what you conclude regarding the consequences of all this, which I think is a fascinating and important discussion. Thanks very much.
Just to say before we move to questions, thank you. That is absolutely fantastic. Really fascinating. I think you should audition for the next Doctor Who, without doubt. And I'm sure loads of questions. I've got about 35 questions, but I'm not going to go first. Let others go first. David's willing to answer questions the next 40 minutes or so. So do ask away.
Yeah, sure. All right, okay, good.
You, all scientists, have measured the age of the universe to 14 million years. Obviously, you're looking back in time to measure that. Have you been able to measure time going forward? How much time we've got?
Well, it's a beautiful question. So what can we say from science about the future? And there's no signal that is coming to us from the future. So time does seem to have this property that we can access the past, but we can't access the future. You know, another way of putting that is that light is travelling forwards in time. So we get signals from things far away, in the past. We don't get any signals from the future. It would be lovely if we did. There are some theories, like you might have heard of string theory, which is a theory of fundamental particles, where there might be particles that can move faster than the speed of light, and they could actually move backwards in time. They're called tachyons. If we could ever get a tachyon detector, and if tachyons really exist, maybe we could get a signal from the future. But right now we don't know how to do that. The only way that scientists can talk about what might happen in the future is if they assume, okay, let's assume that our current theory is correct, that it just carries on like that. If that's true, our simplest theory at the moment about the history of the universe is that when we live, we seem to be in a period where the universe is transitioning to being full of a mysterious form of energy that's making it expand faster and faster and faster. If that carries on forever, it's called dark energy. We don't really understand it. But if that carries on, if that's true, if we're correct about that, and if it carries on the way it's going, then what it means is the universe, the galaxies in the universe will just expand faster and faster and faster away from each other until eventually they all clear off and we can't see any of them and we're just stuck on our galaxy in a pretty lonely universe. That's the way things are going, but like a meteorologist, I can only tell you about the way things are going and project a little bit into the future. What if that dark energy is itself just a local feature and will die off at some stage? We don't know the answer to those things. So there's a huge amount of mystery about the distant future. Other questions?
I read from a very scanty knowledge of quantum physics that a particle can exist in the same place, two different locations. Under those circumstances, it's difficult to see how you can denote a time between one element of mass in one place and one element of mass in another.
Yes.
Can you comment on that?
Yeah, so there are some very peculiar properties of, for everyone here, quantum mechanics is a very important theory in physics, very well substantiated, about what happens with very, very small things. So atoms, particles, all of these things obey rules that don't seem to be, again, a bit like what we've been talking about tonight, which don't seem to be like common sense. And one of the things that I think you're referring to about quantum mechanics is if we ask where a particle is, it's not described simply by me saying, there it is, and it's moving that fast. It turns out that it's more like we have to describe it as having a probability of being in all sorts of places, and having a probability of moving at certain speeds. You can even get funny situations that you're referring to, where it looks as though the particle would have to go in two different directions, and there's a probability of it going in two different directions at once. This is all fascinating. Usually these effects are so microscopic that they won't come into this big picture. If you like, what we're seeing is the average of billions and billions and billions of particles. So while people do worry about this, and there was a talk in my department yesterday about these issues in the early universe, in most circumstances, you can neglect them. Just like in most circumstances, I don't need to worry about the table being in two places at once, because it's the average of many, many particles that could be in two places at once. If I worried about one particular particle, I'd have to worry about that. But because I'm worrying about a big thing with many of those things in it, all averages out to be pretty solid.
So it's all down to statistics.
Yes, it's down to statistics, exactly. Yeah.
Thank you.
There's a question there.
It's always me, David, who asks the awkward question.
Okay.
But I can say on this occasion, you mentioned it first. What about aliens?
Okay, so what's really interesting is that when I talk to physicists about this, and when I find out what biologists think, there's actually a bit of a gap between them. Let me show a diagram again. So when we went to this map, this was a real map of all the galaxies, and physicists get really impressed with this. There are literally hundreds of billions of galaxies made of hundreds of billions of stars, and now we know that many of those stars, maybe most of them, have got planets. And when you start to think like that, you think, okay, so it just seems inordinately likely that there is life on some of those planets, just from a statistics point of view. But the question is, and this is what biologists are interested in, the question is, how hard is it? What's the chance? What's the probability of life starting? We don't know. What's the probability of life developing to become intelligent life? Again, we don't know. But some biologists think that that's actually a really low probability, whereas physicists are just impressed by the numbers here. I don't know what to think. I think that so what I do think is this. This is, at best, the sphere of influence of humanity. Okay? Or another way of putting it is, any alien over here, which was sending us a signal in the last 5,000 years, the light from that alien would never have even got to us. So I think that if there are aliens, and let's suppose there were 3 civilizations in this galaxy alone, then first of all, even if they lived in the same 5,000 year period, we'd never know about them. And also, given the vast range of times in the universe, of billions of years, it's like ships that pass in the night, or ships that don't pass in the night. They might have lived 1 million years ago. We'd never have known. So it may be that there are aliens, it may be that there are even many, many aliens, but the universe is just too big for us ever to meet. But equally, I think it's possible that we're unique. We just don't know. Oh, one last thing about that. For the first time in... we're building this big radio telescope in South Africa and Australia called the Square Kilometre Array. And one of the things that telescope will do is it has hardwired as part of its purpose a SETI program to search for signals from aliens. And it's so sensitive, this radio telescope, that if there's anything like the US military on a planet in the nearest 1,000 stars, okay, so if there's a planet orbiting any of the nearest 1,000 stars, and that planet's got the US military on it, we'll just hear them. They don't have to be sending us a signal, we'll just snoop on them. So it's very sensitive. So at last, although, I mean, the nearest 1,000 stars is nothing, but at least we'll be able to start to put scientific numbers on this. We'll be able to say, we're 1 in 1,000. And then eventually, you know, with future technology, maybe we'll be able to say we're 1 in 1,000,000, we're 1 in 1,000,000,000, and so on. So it is something that science can try to do. It's just really hard.
Is that not making assumptions that an alien life form has got the same technology as us and
Right.
can't travel
Very
to
good.
us at a different rate that we
Very, very
conceive?
nice. Yeah, yeah. So what I've just said is only true if it's like the US military. So in other words, if they're giving out radio signals, then that's what we would be able to detect. But suppose it's an intelligent magnetic field in a dust cloud or something really alien, something very different, that communicates in a totally different way, then maybe we would never even realise it was communicating. That's possible. But if there's any carbon-based life forms, somewhat like us, you know, like the Star Trek universe, using radio waves, eventually we would be able to detect them. But you're quite right, that's only a subset of what might be out there.
It's quite naive to imagine.
Yeah, you know, exactly. Yeah. And it really is sort of searching under the lamp, searching for your keys under the lamppost. Yeah.
Can I come back to your very first question you started with? Besides,
Can I just give you a
yeah,
mic?
sure.
Thank you.
Besides part of it being a measure of decay, what is time?
Oh yeah. Oh, gosh. Have you got any more? So what I hope I've been able to do, so as I said then, you see, one of the problems is the question of what are we wanting when we ask that question? I do ask that question, what is time really? I'm not quite sure what answer would satisfy me. When I ask, you know, what is a chair really, I know what sort of answer would satisfy me. It would be talking about a chair in terms of things that were simpler and that I already understood. So somebody might say a chair is really a board on 4 vertical posts. And I say, oh, right, now I understand what a chair is. But with time, I'm not even sure that there is such a simpler thing that I would feel more satisfied with the answer. But that hopefully it does fit in some theory. So we can start to say how time behaves. So we can say that time behaves like it is something which started with the universe, has gone on a long time. Its flow depends on how fast you're going and how much gravity there is, so it's bound up with gravity. You can start talking like that, and that's what I've done. And that's basically as far as I can get so far.
A lot of, like you said, what we consider time changes all the time relative to what you're doing later. Is it just us trying to get a concept of behaviours of other things? I mean, does time actually exist, or were we just using it because it helps us understand?
Yeah, that's a very interesting question. It's a very interesting question. There have been some physicists who wonder if time is just a psychological illusion. And you could indeed start to look at space and time as just there. Just 4 directions, 3 directions of space and 1 direction of time. It's just there. And we just happen to experience it as something that flows and something that moves. You can take that view. But at the moment we don't know of any experiment or anything deeper we could do to really test those ideas. They just seem to be different opinions or different views that you could hold about what it really is. What you can do is you can write down good theories and good equations for how time behaves and how things behave in time. And that's about as far as we've got so far.
Okay, so
but it's a great question, right? We need to get. I'm not saying it's a bad question, but I am saying that at the minute, as humans, I'm not sure we've got a good lead on it.
Okay, just a quick, simple one. I don't need to hold. You know, when the time's relative when you shoot off in the rocket, how fast you go. Is it dependent on who's moving the fastest? So if I jump up in my rocket and go into the same orbit as Earth, but it's stationary and wait for the Earth to come back, will the person on the Earth be the one that stays younger?
I'll have to think about that particular example.
Okay.
But do you want the answer to why the paradox works?
Yeah.
It's because the 2 people aren't actually doing the same thing. Okay. So the person on Earth, they just stayed put. So they just carried on in a normal situation. The person on the rocket, there's various ways you can slice this. But the simplest way would be, okay, they went fast in this direction, but then they had to slow down, decelerate, and then accelerate again and come back the other way. The person on Earth never had to do any of that business. So they weren't similar, and it turns out that that deceleration and acceleration is what means that the person, he's in the category where he stays young. It's quite hard to see that that's true without all of the theory that Einstein worked out, but that is indeed the answer. And the reason for the answer is that you haven't actually done equivalent things. One of them had to accelerate and one of them didn't.
David, can I go back to what you said a moment or 2 ago about what sort of answer would satisfy us? That's really interesting. And you give the really good example of a chair. The thing that satisfies us about a chair is what it's for.
Great.
What's its purpose? So it's not just this is a plank of wood with 4 legs. It's because it is used by us for ...
Nice, yeah.
And a part of me is wanting to say all the time in cosmology theories, you know about something called the anthropic principle?
Yeah.
In other words, the human brain shapes the universe because that's the only way it can see the universe. So the correlation between what we think the universe is and what is really out there is something we've never quite grasped, because all we can see is the sorts of things that gives us the sorts of answers that we're searching for. And the link between what we can see and the chair, the purpose, is something we really struggle with.
Right. Yeah, thank you very much, that's really great. With my scientific bent, I've tended to focus on this talk on mechanisms and material reasons in that way. Whereas you're asking a very important thing, which is what is time for? And that's extremely important. In fact, I would love to add it to my bullet pointed questions for everybody to think of. But what is time for? That's a great question. Yeah, I agree with everything you just said. Was there a question in there which I've missed? I'm not being sarcastic.
That's the question.
Yeah.
I suppose the question was, is the way we understand the universe just a projection of the human sense of purpose?
Right, okay. So this is a very deep question which I'm not an expert on in the philosophy of science. Okay, so what are these theories that we generate, and what's their relationship to the truth about the universe? I think I land in a box which is called critical realism, where I think that the theories that we make, if they are making good predictions that are then found to be true by experiment, then often, I hope, my model of what is happening is that those theories are picking up on things that are real about the universe. But our theories are always provisional, and they're never perfect in how they're describing the universe. Some people would take very different views and think that these things are completely constructive. Theories are constructs, and it's very hard to say that they're actually related to what's really going on. But I take a more cautiously realistic view. Sometimes we're catastrophically wrong. We need to be humble about that. But most of the time we find that there's an incremental building and converging towards a picture that is making sense of many, many things. I am happy to say that is, cautiously, that is saying something true about the universe.
Can I add to it? Theories, for example, if we take the theory of the solar system, and how that was dependent upon a kind of societal change before they could accept the fact that the Earth was not the centre of everything, because it had man on it. And I think there was a danger in some of the things you said earlier, that we could think of ourselves as being still very important in the universe.
Right.
And there are things beyond that. The other thing is that some of what you were talking about, will change over time as the society accepts these ideas. So general relativity and things like this have not been acceptable because they're counterintuitive. But as people get to understand a bit more about it, then presumably people will accept these things. These are kind of
Yeah.
So I think we're kind of waiting on.
That's right. All of this is developing and provisional. One way I'd put it is we're always in cosmology in this extraordinary mix of rich knowledge and profound ignorance. And it's not as though only one of those is true. Both are really true. So all of these fantastic data, we know so much now about the structure of the universe and about its development and what's happening out there. It's really marvellous to live now. And it's real, we really are getting all of that data. But also when it starts to come to some of the theories and interpretations of that data, there are big, fundamental gaps in our understanding. It's not all cut and dried. I was saying earlier about this dark energy. there really is lots of evidence that the universe, the galaxies are expanding and, the galaxies are moving apart faster and faster. So that's a real effect. And so we call what is causing that dark energy. But calling it something doesn't mean we understand it. It's just a label for our ignorance at the moment. So it's this peculiar mix. We know this really interesting thing about the universe, we really do. But also, there's a lot of ignorance about what it means. I've taken a slight tangent from your comment.
I could be a devil's advocate in saying that some people say that God is the explanation for our ignorance.
Right, yes. Yes. And I think that what everybody here needs to wrestle with, including myself, is the question of where is it sensible or appropriate to invoke God as part of the explanatory system. So some people would say, we see this web of material, God just made it, and that's the beginning and end of the explanatory system. Whereas, as you saw, what I did was I said, there's a simple explanation in terms of dust that collapses, and then one might want to say, and that whole system, that whole theory, the cause of that is what we call God. Sounds a bit like Aquinas. So one has to think hard about where do we want to invoke God. If we invoke God too early in the process, we don't get any understanding about mechanisms. So, but yes, that's right. What you said could be taken either way. I'm not quite sure which way you meant it. One could see it as a critique of the idea of invoking God, or one could say that sometimes where we're ignorant, that is indeed where God resides. I'm open to both of those points of view.
My role is to tease us.
Yeah.
I don't know if I'm qualified even to speak.
Always,
I'm a
please.
totally non-scientific person. I have to tell you that most of that just went straight over my
I'm
head.
sorry.
And I did do some physics at university, believe it or not, subsidiary. But I wanted to say that for us who don't understand all this stuff, time appears to be something by which we explain the way we are born, and everything is born, and does things before we eventually die.
Yeah.
And as we interrelate with other people, it's clear that they have the same system. And I'm quite happy with that.
Yes, yes, and this is very important, right? So and I hope that other parts of this time reflection will think about that. That's about human time. It's absolutely crucial. And in fact, I sort of kicked towards it, towards the end, when I said, is this point of view that the vastness of time is significant? Is that really what's actually significant? Maybe human moments, and maybe that's what we should be focusing on, and not feel intimidated by this vast backdrop. So I do agree with you, human time is really important.
On the other hand, I use the sense that God is beyond time, has no time at all, to explain a lot of the things that are very difficult about religion.
Yeah.
The question I wanted to ask you was, do scientists like you enjoy watching science fiction? Or do you always say,
So,
well, that's the
That's a beautiful question. And the answer is, I haven't been able to work out what it is that means that some films are, terribly inaccurate about the physics, and I love them. And some of them really annoy me. And I can't quite work it out what it is. So, I'm going to alienate quite a few of you, I've no doubt, by my choices. But Gravity, the film Gravity, I loved Gravity. And there's all sorts of my colleagues who are saying, but they got the angular momentum wrong when the person threw the spanner, and it's like, it really annoyed them. But I just loved it. Whereas Interstellar really annoyed me. Basically, I think where it annoyed me was when somebody fell into a black hole and suddenly they're in like a 4D version of their own library or something. I thought, that's not what happens when you... I got really annoyed about that. So I don't know what it is that means that some science fiction, even if it's not correct, I just love it, and some not. Like Doctor Who, I love Doctor Who. I think maybe it's about how seriously they take themselves, right? You know, Doctor Who is not really trying to be scientifically accurate, so I can just take it for that.
What about Star Trek?
Star Trek depends on the day. I do sometimes watch Star Trek. Depends on the episode of it.
We do have time for perhaps one or two more questions, and then I'm just going to let all our throbbing brains ease gently down. But if you do have one more question, now is your moment. Oh, 2 questions, right, hold on. Thank you.
Well, personal reflection on God and where it all began. I think back to the moment of the Big Bang, Planck time, 10 to the minus 43 seconds, when energy became mass. And I have this picture, which I suppose in the Sistine Chapel, you've got
Right.
his finger.
Yeah.
And I like to think, that's where it began.
Right.
And that's my rather not very sensible link, perhaps, towards where Christianity, where God, and where we all came from comes in, and something to do with physics.
Yeah. Thank you. I don't think I need to comment on that. Thank you very much.
And last one.
Not profound, but when Alice fell down the well.
Now, which one was Alice? Was
In Alice in Wonderland.
Oh, right, okay. I thought you were thinking about friends who fell into the black hole.
And fell very slowly.
Right.
Was Carol talking about time?
Oh, I wonder. So I don't...
Time was different for her. She had time to take stuff off shelves.
So I think, our modern view is so this is interesting from a historical point of view. Our modern view of black holes and all of this time distortion originated in, roughly speaking, about 1918 and onwards from there. So Einstein was thinking about this at that time, his theory of general relativity, and Lewis Carroll was before that. Interestingly, people had actually already started to propose black holes because even if you don't have Einstein's theory of gravity, if you've got Newton's theory of gravity, you can still have a situation where light can't escape because there's so much gravity that the light can't escape. But in that view, there was no time distortion. They didn't understand that yet. So I think it's really fascinating, and we can reread Alice in Wonderland in this way. It's very nice to do it. From a historical point of view, it was preceding these ideas, but it's nice as a rereading. Yeah.
David, that's been absolutely fascinating. Thank you so much. Fantastic. I mean, I think part of my answer to the discussion you and Sue are having is you need the poet and the cosmologist side by side. In other words, you're giving us a really powerful view of the universe, but we need to lay other things alongside that to get a full understanding. Perhaps that's where faith, poetry, art, science all come together. That we're all somehow looking at and interpreting the same reality, but through different sets of experience and spectacles. So thank you very, very much. It's been deeply enlightening, absolutely fascinating, and a fantastic contribution to our lecture series. Thank you.
Thank you again.